So it is lecture 6 on moment. In the last video, we see the transformation of random variable. So before starting the moments, I just give an example of transformation of variable for discrete case. So it is just a simple example of discrete case transformation. Example of transformation in discrete case. Discrete random of discrete random. So for continuous, we see how to transform the continuous random variable is like you need that Jacobian thing and that determinant, that thing, determinant of dy dx. But for discrete, say you have a x is a random variable, x is a discrete random variable, say easy, say it is uniform. So x equal to I is just 1 by n, probability I equal to 1 to n. So n is some natural number. Some natural number, say n equal to say 5. Okay, we take other example. So we take it is 2n plus 1, where it is I is from minus n to n. I just change this. Minus n plus 1 minus n plus 2 dot up to minus 1, 0, 1 up to then 2 up to dot n. So if say n is say 3, we take minus 3, minus 2, minus 1, 0, 1 to 3. Each probability is 1 by 7. So it is uniform. Now we have a transformation. Say we transform this random variable y, x to y, say x squared. Our function is x squared function. So y is fx. That transformation. Now what is the probability of now what is the spectrum of this x? What is the positive probability assigned to the x? So it is called spectrum. Spectrum of x is a positive probability assigned to the x, which is minus n plus 1 up to minus 1, 0, then 1, 2 up to n. So this is the spectrum of x. But what is spectrum of y? So if we say for example, say n equal to 3, so it is minus 1, minus 3, minus 2, minus 1, 0, 1, 2, 3. So then the spectrum of this is just 0, 1, 2 square, 3 square up to n square. So there are n plus 1 many value in the spectrum, because 3 square is again 9 and 3 square is 3 square is 9 and minus 3 whole square is also 9. So for n equal to 3, it will give y can take only values positive probability 0, 1, 4, 9. So only 4 values. Here only n plus 1 values. Now what is the probability? What is the distribution of y? It is clear that distribution of y equal to 0 is 1 by n to n plus 1, because it is only one value 0. But probability of y equal to other values, say other I square, for I equal to 1 up to n, not I not equal to 0, it is 2 by 2 plus n, because y equal to I square is basically the y equal to I square, that set. It is a set. Remember, y equal to I square is a set. Is y in f inverse of that thing, that x equal to, what it is a set basically. So what is x equal to 5? That means that inverse thing, that all omega such that x omega. So such a thing is there. So it is actually it is union of two things, x equal to I and union of x equal to I is again a event, a set. So x equal to minus I. So that's why the probability will be adding of these two, this plus this. So these two are disjoint, x equal to I and x equal to minus I, because I not equal to 0, I from 1 to n, and rest other values it is 0. Other than that, say if I take 2, or if I take n plus 1 whole square, then it is 0. The spectrum is this, means the other value of, other than the if you take any other value outside from the spectrum, that then probability is 0. So this is an example for the discrete case. In discrete case, you have to just merge the probabilities. Continuous case is slightly different. It needs some calculus or integration thing, derivative, such a thing. So in discrete, it is easy, but you have to be very careful about that. Now we are going to the define the different moments, expectations and moments. So different moments. So we define, let's say x is a random variable. So x is a random variable. So it is a discrete random variable. Discrete random variable. Then what is the definition of expectation of x? It is just sum over all x into probability of x equal to x, and that x must belong to the spec of x. Remember that. That spec of x is either finite for finite random variable, or it is countable for infinite discrete random variable, And for continuous, it is different. But we in our syllabus, there is no mixing of this discrete and continuous, not mixing. So we have three type of thing. One is just finite. Finite is obviously discrete. One is infinite discrete, which must be countable. Spec is we've already proved that spec x for discrete and variable spec is at most countable. We already proved in the previous video. So it's maybe countable or is finite. It can't be uncountable. For continuous, the spec, there is no concept of spec, there is a concept of support. So this is maybe a finite sum or maybe a, so whatever. So this expectation of this, now this summation may be a finite sum. It may be a finite sum. It may be maybe finite sum, or maybe it's a series, finite sum or a series sum. Now if it is a finite, no problem. If it is finite sum, no problem. But the question, if it is series, now question, if spec of x is a countable set, then what do you mean by this set? Then what is meaning of that summation? That's the problem. What do you mean by this? The two problem. The problem is there are two problems for defining that summation. The first problem is it may not be converged. So if this is a series, that sequence, that sum of that series may not be converged. So there are different issues, like, so that is may not converge. And another issue is this. So okay, let's spec say our spec of x is just some element of x1 x2 or dot 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 is a countable set. Is a countable set of is countable subset of R. Now it may be say 1 2 3, like for Poisson it is 0 1 2 dot 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 dot. For binomial, Bernoulli, hypergeometric negative binomial, these are finite. But for Poisson or geometry, these are infinite. For it is 0 1 dot dot dot. Now question is, which term you will write first? So should I write expectation of should we write expectation of x like x1 probability of x equal to x1 plus x2 into probability of x2 in that order, or we write in this order? Say expectation of x, say first I write x2, then x1. Which order we write? Then say we write x4, then we write x3 term. In which order we should write? The question is, this two things are different. So the important question is a1 plus a2 this series, is it equal to say a2 plus a1 plus a4 plus a3? Is this two are equal? This is a very important question. Is this two are equal? You can say that, okay, I write x1 first, then 2, then 3, but the number may not be like that. Number may be √2. So x1 may be √2, x3 may be e to the power pi, x3 may be sine 1 minus cos 1, something like that. So which number you write first and which number you write second in the series? Now, question is these two are same? The answer is no. Unfortunately, the answer is no. These two are not equal. Yes, if all terms are positive. If all the terms are positive, then it is yes, obviously yes, and obviously that not only that should be converged. Yes, if this positive and this sum is converged and summation ai is finite, it's converged. If this series sum is converged and this all the ai's are positive, then it is true that if you rearrange the term, then sum will not be affected. The sum will be same for the different rearrangement. It's called the rearrangement of the term. But the answer is no if some AIs are negative and some AIs are positive. Negative and some AIs are positive. Even if this series is converged, then answer is no. So what is the meaning? The meaning is that you have an example that there are some examples. So there exists some xi real number, may not be there's some are positive, some are negative, such that this sum converge. This sum converge. This converge, but that sum is finite. Converge to say L1. And this rearrangement of the terms, say x a1 f2 plus a3 a4 plus a3 first even they not, that also converge. Both the series converge. If one of the series does not converge, this series is a divergent sequence or divergent series, or it is not converged to any finite number, then obviously this cannot be equal, because that limit does not exist. Since limit does not exist, that cannot be equal. But even if the limit exists, then also L2 may not be equal to L1. We can give an example of such a sequence of positive negative term, sometimes called alternating series, that L1 and L2 are different. Like one of the example is like that, it is called alternative harmonic series. This series converge. This series converge to some number which is called gamma. With this number is called gamma. And if you just rearrange your term, if you have some other rearrange, another rearrange, if you have some other rearrangement of term, rearrangement of the terms may converge to a number, to a real number, which is different from gamma. This may happen, and such a sequence which is converge, but it's some alternatingly maybe positive negative. But if you rearrange the term, it's converged to a different number. So that means your 1 minus half plus 1/3 minus 1/4, that is not same as if you write the different way. So if you say 1 plus 1/3, then minus half, then you take 1 by 5, the two odd terms, then one even terms. You can rearrange that. You take first one first, the third one second, the second one in the third. Then the fifth one is the fourth, seventh one in the fifth, and the fourth one in the sixth. In that case, this also converges, but it's converged to a different number, not converged to the gamma. It's not converged to the gamma. And there is a theorem, you can rearrange such a way that you can converge to any real number. This is interesting. This is an interesting theorem by Riemann that in this series, in particular alternative harmonic series, if you give me any number, see, you give me 1, I can rearrange the term suitably that that series converges to 1. I can suitably rearrange the term such that that series converges to 0. I can suitably rearrange the term that can be converged to the 1 crore. I can suitably rearrange the term such that this series, that after rearrangement, may converge to the minus 2 lakhs. And I can rearrange the term suitably such that the series does not converge to the diverge to the infinity. And I can rearrange the term like that the series converts to the diverge to the minus infinity. Any number you can convert just to rearrange the term. So now the question: if you rearrange the term, then the expectation will be different. Then for a in the definition of expectation, which term I will take first? If I take the x1 first, or if I take the x2 first. So if there says in spectrum some number may be like that, say root 2, one is root 3, one is say root 2 plus root 3. If someone take root 2 first, root 2 says root 3, then minus root 5 in the say third term. If someone takes a root 5 minus root 5 in the first, then they will get the different sum. So what will be the sum of the expectation? Actually, the definition of the expectation, that's a problem. That's a question. So there is two issues. It may not converge, and if it is converge, if you just rearrange the term, may converge to a different number. So that means to define that expectation, you just if you say, okay, I define this expectation like that. Okay, if I say our spectrum is my spectrum is say x1, x2, maybe some negative, positive, or any other. You can, this is a set, basically it's a set. You can write x2 first, x3 second. So expectation of if we just define like that, I equal to 1 to infinity, xi into probability of x equal to xi, that creates a problem in two way that may not be converged. Even if it is converged, if you realize the xi is different, say x10 first, x3 second, then it may could convert to a different number. So just if you take, okay, we define this, provided that series is converged, provided that series is converged. If I is converged, okay, first, okay, we define this is an inspection so that this is converged. Then also there is a problem, because if I rearrange, that may not converge, or if it converges to a different number. So this cannot be the definition. This cannot be the definition. The expectation of x cannot be defined like that. I equal to 1 to infinity xi, probability of x equal to xi, provided that series. This is a converse to 5. You can't say that expectation is 5 because someone can rearrange the term and he can get, he or she can get 7. Now, this is a very, very important result. Is this? If all the term are positive, the result is, the theorem is this: if all xi is ai is positive, and this is a converge, this series converge, then any rearrangement of terms after any rearrangement of terms, the new series converts to the same number. That's the interesting thing. So if all the terms are positive, if you rearrange, then is one is converged, then if you after rearrange, they converge and converge to the same number. But for negative, positive, some negative, some positive, is not true. If such a thing happened that if say if this is converge, but if you take the positive term, the mod value of this, it does not converge. If may happen for the harmonic series, this converge, this harmonic series converge, this converge, but 1 plus half plus 1/3 does not converge, this diverge. In that case, we call this is called conditionally convergent. Then we say this summation is conditionally convergent. Conditionally converge. And if that is converge, this mod value, sum of the mod value converge, then automatically that converge. That series converge. This is interesting. It may be the sum of the AI converge, some of mod of summation AI may not converge, but the other is not true. If summation AI is converge, mod AI is converge, then must that summation AI is converge. Now, if this is converge, then this also, and we say this summation is called absolutely converge. Absolutely converge. So if I say that some series is absolutely converge, it means the series is not only the series is converge. If you take the mod value of the each term, then that series also converge. And if I say the series is conditionally converge, that means the series is converge, but if you take the mod value of the term, then it is not converge. Now, once it is if it's all the positive number, then there is no question of absolutely converge condition because all are positive. So if it's converge, then it must be absolutely converge. If all the terms are positive, even if some finite term are negative, rest are positive, then also no problem. Finite term are positive, all the rest are negative, then also no problem. Finite term are negative, rest are positive, also no problem. But the infinite terms are negative, infinite terms are positive, then may create some problem. Now, this is called absolutely converge and conditionally converge. Now, if some sequence is absolutely converged, then one more result is this. If this series, now one theorem is this, if summation AI is absolutely converged, what is the meaning of that? That means the mod value of AI is converged. Then rearrange of the series converge and converge to the same number, to the same limit. This is interesting. Now, if it is absolutely converged, then you can rearrange the term. So that means to define expectation, just the summation of that is converged is not sufficient. You need the extra condition that it is absolutely converged. So definition is definition of so definition of expectation of x is this. So definition of expectation of x is this. So for the discrete random variable, x is a discrete random variable, and spec of x is just x1, x2, dot, 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 dot. That is a spec. That is a countable set. It is finite, no problem. If all the terms are positive, no problem. If some terms are negative, some finite terms are negative, rest are positive, no problem. The problem is some are positive, infinite terms are positive and infinite terms are negative. In that case, the problem is that you can't just define the expectation like that. You can't define the expectation like that. You can define the expectation like that, provided you have a need extra condition, provided that summation not only the xi, that mod of xi into probability of xi, that must converge, provided this converge. Once this converge, this series converge, this is absolutely converge, and in that case you can rearrange the term. This is converge and rearrange the term. After rearrangement, the sum is be same. So you can now, since it is same, you can say, you can rearrange the term. You can say x2 first, x1 second, whatever may be. Ultimately, the sum is the same number, and that number is called the expectation of x. So to find the expectation of x, you first check. You have to first check whether the mod of xi into probability of x equal to xi, this series converge or not. This summation converge. You have to first check that. If it is not converge, you just say the expectation does not exist. There are two steps. See, first step, you have to check whether x, some mod of xi into probability of xi, that summation exists or not. If it does not exist, if it is divergent, it goes to infinity, you say expectation of x does not exist. Okay, we find that is finite. It's a 10. You should not say that expectation is 10. You have to find the, now you have to find the summation of xi into probability of xi. That may be 7. The expectation of 7. Two expectations may be, two summation may be different. That summation xi into probability of x equal to xi, that summation, and summation mod of xi into probability of x equal to, that is obviously different, because some xi are negative. For the that absolutely that mod value series, that we take all the positive term, get the mod. So that may be, must be, so obviously this is less than or equal to this, and obviously it is strictly less than if some terms are negative. If some xi's are negative, then obviously this is strict inequality. Strict inequality. Because in the right hand side, every term is positive. But in the right hand, left hand side, the positive term are equal, but the negative, some are negative. And obviously, if all the x's are positive, then no need of checking that mod value. So that is the interesting thing, and we should say the expectation of x is this, provided that now series is converged. Sometimes we write that as a expectation of mod x. Expectation of mod x is like that, is this. So we say expectation of x is this, provided that expectation of mod x is exist. Obviously, expectation of x and expectation of mod x may not be equal. If they are equal, if x is itself the positive random variable, and some terms are in spec, some terms are negative, then expectation of x and expectation of mod x is different, and expectation of x is strictly less than expectation of mod x. So this is a definition of expectation, and the more general expectation defined like that, the definition of, so expectation of gx, g can be any function. Function of g is a function from real to real. Obviously, it's a measurable function. Otherwise, measurable function. Eventually, it's a Borel measurable function. It's measurable means it is a Borel measurable. Unless if it's not a Borel measurable function, then if x is random variable, x is a random variable. Then if it's a Borel measurable, then gx is also a random variable. We already proved that is a random variable. So if it is not Borel measurable, then may not be that gx may not be a random variable. So now we consider that gx as a random variable, and that aspect of gx is defined like that. So it is, again, it is a discrete random variable. X is discrete random, which is finite, no problem. This x belongs to all spec of x. Other than the spec of x, all the probability is 0, so we should not take that sum in the assumption, because it just plus 0 plus 0 plus 0 like that. So now it is gx I, or is xi, or okay, say it's just x. It may not be some. Sometimes we will not write xi. All x belongs to gx into probability of x equal to x. But again, one more extra condition is important, needed. So provided that summation is this summation mod of gx into probability of x, this converge. You need that extra condition. If this is not converge, even if that summation gx probability of x equal to x, that's converge, we say that no, this is converge, but we can't say this is the expectation of gx, because the more expectation of mod gx is, this is actually expectation of mod gx, that is not converge. Otherwise, if it's not, this is not converged, the second one is not converged, the first one is converged. If you rearrange the term, then your expectation of gx will be different for the different rearrangement. And obviously, what is the variance of x? The variance of x is nothing but the expectation of x minus expectation of x whole square. That is the definition of variance of x. So it is just summation x belongs to spec of x minus expectation of x. We have this expectation of x is a real number. Remember, the expectation of x is a real number. It's not a random variable. It's a real number into probability of x equal to x. Oh, sorry, whole square. And we know that this is also the equivalent form, that is xi x square probability of x equal to x minus expectation of x whole square. That is also equivalent form of this variance. And we know that other different moments, the raw moments or this other moments, the mu r of x is sometimes called as a center moment or raw moment. Is called raw moment. Say the different notation are okay. It's a raw moment. So raw moments are this, nothing but it's an expectation of x to the power r. By the way, for the variance, you need not to check that provided that thing. You need not check because there is square. But for this is just expectation. This is summation x belong to spec x to the power r probability of x equal to this is raw moment. Provided again the provided this summation mod of x that maybe that r, if r is odd number. Oh, by the way, that r is a natural number. We should not take the r as a fraction. That is converge. That converge because r may be the odd power. If it is odd power and x is negative, that cannot converge. So this is converge. This is called raw moment. Then you know the other is called central moment. Is the expectation of that x minus expectation of x whole to the power r. Again, this is defined provided that blah 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 blah. So that mod value is absolutely converged. So this is the different moments, raw moments, and similarly you can define the skewness. Kurtosis is like the same way that third moment, fourth center moment by the divided by the second center moment whole square is the kurtosis. We know that theorems, the definitions. Now for the again, now for the x is a continuous random variable. What happens if x is continuous? Now the problem if x is mixed type, continuous and discrete, then this is not in the syllabus. So x is continuous random variable. Then expectation of x defined like that. It is integration over minus infinity to infinity, or with PDF fx. Then it is x into fx dx. Again, it's provided this mod of this. Oh, sorry. This PDF provided this converge. Provided this converge. Once this right hand side converge, then once some integration of the mod x fx dx converge, then obviously we can prove that x fx dx converge. So provided this is converge, you first have to check whether this is convergent. And what is called the support? Support of x is, in that case, what is the support of x? In that case, we call support of x. Support of the SUPP support of x is set of all x and the real numbers so that your PDF is positive. So PDF is positive. This is called support of x. And obviously you can write the expectation of x in this notation. It is just on the support of x. You just have to integrate on the support of x. Obviously, the provided this is that absolute thing is integration is converged. Similar for the if gx is a again if gx is a g is a function from real to real, is measurable that means Borden reversible function, then expectation of gx is defined like that. This is integration over the minus infinity to infinity, or you can just write the support that gx into fx dx, and again provided that integration mod gx fx is positive. Remember, fx is positive, pdf is positive, so we need not take the mode of fx. Mode of fx is same as fx because fx is positive or 0. It can't be negative. pdf can be negative provided this is finite. This. So similarly, you can define the variance. So variance of x is just expectation of x minus expectation of x whole square. That is integration minus infinity to infinity x minus expectation of x whole square fx dx. Similarly, the different moments and different units, Cartesian, other all are you can define in a similar way. But one thing is this: for this countable discrete, you need to handle this series, absolutely convergent of some absolute convergence thing, or convergent of series rearrangement. This you have to handle all these things. But for continuity, for continuous random variable, there is a different problem. So we need to know what is the meaning by this integration. Basically, what is the meaning of this integration? What is the meaning of this integration? This is basically an improper integral. This is not a proper integral. This is not a Riemann integral. This is called improper. This is called improper integral. Now, there's improper integral. There is two kind of improper integral. That one kind is the limits are infinite limits, so 0 to infinity or minus infinity to infinity, like that. And another type of improper integral like that, so it's called type 1, and then next one is called type 2. Set is some point in some, say, x tends to 0 plus, that fx is itself infinite. So limit x tends to 0, fx is infinite, does not exist. Or limit x tends to 5 minus fx is infinite, is not or minus infinity, or it's not finite now. Then like if your pdf is like that, if your pdf is like that, say this pdf is like say this and this, you have something like that, there's infinite and then 0. If pdf is like that, then the question of what do you mean by actually minus infinity infinity integration? So we need to define that in the improper integral. We already defined. I just briefly recapitulate this. So if it is a kind of there is no discontinuity. So if it's continuous, if you take the if it's continuous function, then this limit, this is actually defined like that. This is improper integral of the first kind. This is limit m tends to minus infinity m to 0 fx dx plus limit, it's the limit n tends to infinity. You have to break in the two part, minus infinity to 0 plus 0 to infinity, n tends to plus infinity 0 to n fx ds. If one of them limit does not exist, then we say this limit that left hand side integration does not exist. So left hand side integration exists, is that improper integral exists if the both limit exist and finite. You sometimes use you see that there is one more definition like that. So minus m to m. But this is not integration fx to dx. This is actually not equal to integration fx. This is not equal. Sometimes the left hand side is called the Cauchy value of this improper integral. Sometimes the left hand side is called the Cauchy value of this left hand. If I say that what is the Cauchy value of this improper integral, then actually we mean the limit x tends to m tends to infinity minus m to m fx dx. But some improper integral, the Cauchy value may exist, but the actual that improper integral may not exist. Individually, that thing may not exist. Like say x, if you integrate x, if you integrate minus m to n x dx, this is 0 for all m. 0 for all m. Now, if you take the limit m tends to infinity minus m to m, this goes to this is 0 for. But if you take the limit in a two different way. So limit m tends to infinity, 0 to infinity, that does not exist. So if I ask the what minus infinity to infinity x dx, is this improper integral exists? You say no, this improper integral does not exist. If I say ask that what is the Cauchy value of this minus infinity to infinity x dx, you say it is Cauchy value is 0. The Cauchy value of this improper integral is 0, but this improper integral does not exist. This integration does not exist. So I'm not going to details in this because in the part of the real analysis, but we have to know this. Otherwise, you can't find this expectation. You have create some problem for finding the expectation of some random continuous random variable, like Cauchy random variable. This is one type, and the another type of continuity is like that, like a beta gamma function. You know what is beta gamma function? It's a beta function is like gamma function is like that. You know this is a gamma function. This series converts for n greater than 0. This is called gamma n. And one is called there is a one more thing. Say what is 0 to 1? No, it is 0 to 1. Yes, x to the power n and 1 minus x to the power n. This is beta function. And in this is not a type 1, it's type 2 because your limit is bounded, limit is not unbounded. But x to the power 0, if n and n both is greater than -1, so m and n are say -half. Say n is -half. What is the meaning of that? X to the -half? It is 1 by root x. But x tends to 0, 1 by root x does not exist. X tends to 0 plus 1 by root x is infinite. Finitely it will not exist. Similarly, x tends to 1 minus x whole to the power -half does not exist. So in that case, it is called the type 2 improper integral. And again, the limit is if this 0 and 1 is the type 2 thing, then you have to limit in two different parts. First part from 0 to half, and another part from half to 1. But you can't take the 1, you have to take the limit of that, the limiting sense. So you can't take 1, you have to take 1 minus delta, and you take the limit delta is to 0 plus, because you can't go right side of the 1. And similarly, you have to take from epsilon, and epsilon is to 0 plus this function. This is the both limits should exist. Otherwise, if the one limit exists, another limit does not exist, then you say this integral does not exist. This improper integral of second kind does not exist. So you have to break somewhere. Again, if you take the delta tends to 0 plus 0 delta to 1 minus delta, this is a Cauchy value again. It's a single limit. Now it will so happen that your thing is that it's a mix of two kinds. So it will so happen that your function is like that, minus infinity to infinity fx dx, and again your limit extends to say c, fx does not exist. Then what will you do? You will do first, you have to break this in the, you have to take one d, you have to take one d before c, and one, or say a, and another b after c. Now you have to take the four different part. Then this one, then a to c, then c to b, and then b to infinity. Now you have to take the four different limits. For minus infinity to a, there is no problem with a. That is a limit m tends to minus infinity, that thing. From a to c, there is no problem with a. You have to take c minus delta, and delta tends to 0 plus. Then c to b, it is c plus delta to b, delta tends to 0 plus or epsilon plus. And then b to infinity, and where again b to m, m tends to infinity. That you have to be in the four different part, and then if it is so happen that is a function, there are two discontinuity, 0 and say 1. Then you have to break in the six different thing, minus infinity to say -1, -1 to 0, 0 to half, half to 1, 1 to infinity. So sorry, 1 to 2, then 2 to infinity. Six different parts. If one of the part is not defined, then whole integration is not possible. So this is the idea of improper integral. I just stop here now. What is the I say what is the definition of the different moments of the for the continuous and discrete case, and when it is exist and when it does not exist. You can find all the expectation and moment for the different distributions like Bernoulli, like binomial, normal, Poisson, hypergeometric, and whatever beta, gamma, chi square. You can find using that definition. That is all in the book. I just defined the expectations, moments, and one issue is still there. The issue is this slightly complicated. So one issue is this: if you transform a variable, there is a issue in the transformation. Say x is a discrete random variable. You transform that, then it is again discrete. So if x has say spec of x say 10 values, after transformation it may be 5 values or 2 values or maybe 10 values. It can be more than that, because the function from 10 value cannot be mapped into 11 values. Okay, next one, if this x is an infinite discrete, so your spectrum is a countable set. After mapping, that set may be finite. After transformations, like gx, the spectrum of gx can be finite. And but the problem is this is not problem. So x is countable, after transformation is finite. Okay, good. Which is finite, good. The problem is this: so x is a continuous random variable. After transformation, gx is continuous, no problem. The problem is like that: say x is continuous, but after transformation like that, the gx is discrete. Then gx is discrete. Then the problem begins. So, what is the definition of the spectrum of gx? The spectrum of gx is integration gx fx dx. But that if you consider gx as a random variable, that gx is a discrete now, then you should write the summation gx, the probability of gx equal to x. Then what do we write? Whether defined like integration of gx dx fx dx, like with the gx with the multiplied with the pdx of x and then integrate, or we just find the distribution of gx, which is a discrete distribution, take the probabilities of that each probabilities and then multiply the gx and take the summation. So that is the integration or it is a summation. Or if transformation like that, your x is continuous, gx is discrete, then what is the definition of expectation of gx? Whether it is defined by a integration or we define by a summation. That's the problem, but in our syllabus that issue is not arise. We should not discuss this type of transformation where the continuous random variable goes to a discrete random variable. That is not in the syllabus, but remember, if this continuous random variable after transformation goes to a discrete random variable, then this issue will be arise, and you have to settle down that issue whether it is a summation of this thing or it is an integration if gx is discrete but x is continuous. Up to this for today.